Hello everyone. My name is Jesse Ratzkin. I work for the University of Würzburg in Germany. Today, I'm going to tell you about a compactness theorem in the moduli space of singular constant Q-curvature metrics on finitely punctured spheres. And before I begin, I would like to thank Hujili for organizing this festival. So the theorem I'm going to tell you about is joint work with Jean-Enrique Andrade, who is at the University of Sao Paulo, and João Macostao, who is at the University of Paraíba. They're both in Brazil. So I'd like to begin in this first part of the presentation with some basic material and introduce enough so that we can state and understand the theorem. So the object we are interested in is something called the fourth order Q-curvature. And this is well defined for a Riemannian manifold of dimension greater than or equal to 5. It's given by some curvature terms. The leading order term is minus the Laplacian of the scalar curvature. There are some zeroth order terms, which are a multiple of the length of the Ricci tensor squared and the scalar curvature squared. There's some coefficients here, and it's not too important exactly what these coefficients are. Just know that there are some coefficients. They depend only on the dimension. The Q curvature transforms very nicely under a conformal change of metric. What does this mean? This means that if I write down a conformal metric g tilde is u2 to the power 4 over n minus 2 times g, then the Q curvature of this conformally related metric is determined by a certain fourth order operator here applied to u. This fourth order operator is a nice elliptic operator. Its leading order term is the bi-Laplacian, and it has a second order divergence term, and then the constant term is the Q curvature of the background metric. This whole setup should really remind you very much of the classical picture for scalar curvature. And what is the classical picture for scalar curvature? It says that when you do a conformal change to a metric, the scalar curvature transforms according to a differential operator, which is a conformally invariant version of the Laplacian. So in the scalar curvature setting, the operator is basically minus the Laplacian plus a multiple of scalar curvature, and then the scalar curvature conformally related metric is determined by L applied to U. Now, motivated by this parallel, many people have tried to prove results in the Q curvature setting, which mirror all of the results in the scalar curvature setting. And the fundamental problem, which to my knowledge is still open, is the following Yamabe type problem. Given a compact Riemannian manifold without boundary, can one find a conformal metric within that given conformal class with constant Q curvature? There's been some partial progress on this. This smooth Yamabe type problem is very strongly related to the work I'm going to tell you about, but it's a little bit distinct as well. So the two topics are intertwined. I can rephrase this constant Q curvature problem as a PDE, And the PDE in question is the Paneitz operator P applied to U is a certain multiple of U to the power n plus 4 over n minus 4. And this PDE is a nice elliptic PDE. It's fourth order. The one complicating thing about it is that the PDE exhibits critical Sobolev growth. And we're going to see in a minute what the critical Sobolev growth means. So the good news is that because there's an extensive literature attached to scalar curvature, the community has a good model for what we might want to prove and how we might want to prove it. And the bad news is that we see a lot of the same difficulties. And one of those difficulties is the fact that the conformal group of the sphere is not compact. And this non-compactness leads us very naturally to the blowup of sequences of solutions. And I want to illustrate that with a very simple example. And the simple example is to take the spherical metric. So the spherical metric is given in after stereographic projection as this particular conformal factor here times the Euclidean metric. So one can verify indeed that this this spherical conformal factor satisfies the right PDE. But if I rescale by any lambda, so you should imagine this transformation geometrically as first translating, which is not too interesting, but then applying a conformal dilation to my metric, dilating my metric. And when I do that, I obtain this new family of solutions here, parameterized by the thing to pay attention to is really this lambda. And what happens when lambda goes to 0, I see that away from my base point x naught, my conformal factor goes to 0. But near x naught, my conformal factor blows up. So when lambda is very small, the profile of this conformal factor looks very much like a tall, thin spike sitting out of a flat Euclidean space. And geometrically, what is this doing? This is taking the equator, the equatorial n-1 sphere, and pushing it up towards the North Pole. And it's essentially making the southern hemisphere artificially big and making everything in the northern hemisphere very, very, very tiny. So it's this exact blow-up phenomena that forces one to always consider singular solutions, even if before you do any sort of thinking, you're only interested in smooth solutions. This exact blow-up behavior forces you to consider solutions with point singularities. So we are now motivated to phrase the following singular problem. I like to think of this as a boundary value problem where the boundary values happen to be infinity. So what is the setting? I start with a closed Riemannian manifold, a compact Riemannian manifold without boundary, MG. And I take a relatively closed set, capital lambda. And what do I want? I want a constant Q-curvature metric, which is conformal to my, I want a constant Q-curvature metric G tilde, which is conformal to my original metric. And I want this metric to be complete on M minus lambda. And if I rephrase that as a PDE problem, I end up with a function on M minus my singular set lambda, which I want to be positive because I want it to be a conformal factor of a metric. It must satisfy this PDE. And I want the limit as x goes to any point on the singular set of U to be 0. I mean, sorry, to be infinity. I want the U to go to infinity very strongly as I approach the singular set. And this is the problem we're going to concentrate on. Specifically, I want to take my background metric to be the round metric on the sphere. And I want to actually take my singular set to be a finite number of points. It's going to be some finite collection of k distinct points. My capital lambda is going to be P1 through Pk. And if I take this setting, I want to define two moduli spaces of solutions. The first moduli space is going to be the marked moduli space, where I specify the position of all the punctures of all these singular metrics. And the second moduli space is going to be the unmarked moduli space. And in the unmarked moduli space, I don't specify the position of the punctures. I only specify the number of the punctures. So obviously, in a sense, this unmarked moduli space contains the marked moduli space. And I want to place the Gromov-Hausdorff topology on both of these moduli spaces. Okay, so before we continue, it's good to talk about some examples. There's a classification theorem by C.S. Lin, proved in, I think, 1998 or 1999, which says that any regular solution on all of Rn must be one of these dilated, translated spherical solutions. So what does that tell you? That tells you that if I don't have any puncture points, then my solution must be the metric of the round sphere up to a conformal motion. So that's what this says. This says modulo conformal motions. The only solutions with 0 punctures are the standard round metrics. He also proved in the same paper that there are no one-ended solutions. So this M1 is actually the empty set. And if I have a solution with 2 punctures, then that solution must actually be rotationally symmetric. This is after a normalization to move the 2 punctures to be antipodal. Later on, actually much later on, Frank and Koenig classified all the 2 punctured solutions, and we're going to discuss those in a fair amount of detail in the second part of the presentation. And they showed that these solutions corresponding to the 2 puncture metrics are actually parameterized by a neck size, a number epsilon between 0 and some maximum neck size epsilon n. It's a consequence of the fact that n is greater than 4 that this maximum neck size is actually less than 1. And so in this way, you see that when P and Q are distinct points, this MPQ, the marked moduli space, is actually a half-open interval. And now it's time to state the main theorem. So before actually stating it, we have to say that near each singular set, near each singular point, near each of these puncture points, my metric looks very much like one of these Delaunay metrics. Looks very much like one of these singular ODE metrics, singular metrics classified here by Frank and Koenig. So what does this mean? This means that, and again, this is something we'll state more precisely in part 2 of the talk. This means that one can associate an asymptotic neck size to each puncture. So I should remember that I have a metric on a finitely punctured sphere that has constant scalar curvature, positive scalar curvature and constant Q-curvature. And that then at each of these puncture points, I can associate an asymptotic neck size, which is some number epsilon between 0 and 1. Okay, so what does our theorem say? Our theorem says that any subset of the unmarked moduli space such that the spherical distances between distinct puncture points is at least delta 1 is bounded away from 0, and that the asymptotic next sizes are also all bounded away from 0. They're greater than some delta 2. This set, capital omega, within the moduli space is sequentially compact. So what does that mean? That means if I take any sequence of metrics within this particular subset of the unmarked moduli space MK, I can find a subsequence which converges with respect to the Gromov-Hausdorff topology. So our theorem here is very similar to a theorem Dan Pollock proved in the scalar curvature setting. And in fact, our proof is very similar to his proof. It will suffice, we'll see this in more detail later on, but it will suffice to show that I can extract a subsequence of these conformal factors. So remember that my metrics are all conformal to the round sphere. So I can write each GI as UI to the power of 4 over n minus 4 times the round metric. So it'll be sufficient to show that I can extract a subsequence of these conformal factors which converges uniformly on compact subsets. And this will end up implying the convergence within the Gromov-Hausdorff topology. So I'd like to close this first part of the presentation by unpacking a little bit what this theorem says. So this theorem says that a sequence of metrics within my moduli space can degenerate in only one of two possible ways. So what are the two possible things that can happen? Remember, I have some finite number of punctures, and associated to each puncture, I have a next size. So the two things that can happen are one of the next sizes can go to 0. And the other thing that can happen is that two of the punctures can come together. So what does this mean? This means that one can imagine trying to compactify the moduli space MK by gluing on copies of ML for each integer L less than K. And this gluing procedure is actually very topologically complicated because for each L less than K, I can imagine obtaining copies of that moduli space in many different ways, because I could have things like punctures coming together in many different ways. I could have different sequences of next sizes going to 0. So the topology of this compactification is actually probably that of a stratified space. But nonetheless, this is instructive because it tells you that you can only degenerate in moduli space in certain very specific ways. So I've drawn a picture of this in the following. I start with something with 4 punctures. This is in the moduli space M4. So I have a puncture P1 with next size epsilon 1, P2, puncture P2 with next size epsilon 2, a puncture P3 with next size epsilon 3, and a puncture P4 with next size epsilon 4. This can degenerate where two of the punctures here, P1 and P2, can coalesce, they can come together, or this next size epsilon 4 can go to 0, in which case that puncture essentially disappears. So those are the only possible things that can happen. As a preview of what we're going to see in the second and third parts of the presentation, in the second part, I will discuss some of the tools. Primarily, I'll describe the Delaunay metrics, and I will also describe an associated Pohozaev invariant. And this Pohozaev invariant is actually only part of this full Pohozaev invariant, which I'll talk a little bit about as well. And then the third part, I'm going to sketch sketch a proof of the main theorem. And I will concentrate in that sketch on why it is necessary to bound all of the next sizes away from 0. What does that mean geometrically? So this talk will be continued. Thank you.